Hello my friends and welcome back to the Today Machine channel. In rocket manufacturing, the process begins with the precision cutting of metal components using a laser cutter, which ensures that each piece is shaped to exact specifications. The components then move along the outfeed conveyor to maintain an efficient workflow. Rocket design and philosophy. Chris Kemp, the co-founder and CEO of Astra, began his work 5 years ago with the goal of creating a low-cost rocket solution to address the needs of companies aiming to launch satellites into low Earth orbit. By collaborating with Dr. Adam London, they realized the opportunity to scale rocket production by leveraging the economies of scale, similar to automotive manufacturing. The objective was to rapidly and cost-effectively build rockets for the growing demand for satellite deployment. These parts pass through a centering device, which aligns them accurately for the subsequent processes, followed by the barrel roller, which shapes the cylindrical sections of the rocket, particularly the fuel tanks and structural bodies. Astra's design philosophy centers around simplicity and scalability. The company avoided the use of exotic materials or complex technologies like 3D printing or composites, focusing instead on commonly available components. The result is a two-stage rocket designed for small satellite launches. The components are then conveyed to the friction stir welder, a critical machine for joining metals, especially aluminum alloys, without melting the material. This technique creates strong, defect-free welds, ideal for withstanding the extreme conditions of rocket flight. Prior to welding, the materials undergo weld prep, a step where surfaces are cleaned and beveled to ensure a smooth, continuous weld. For the rocket's cylindrical tanks, a circumferential TIG weld, tungsten inert gas, is used. This high-precision welding method creates strong, clean joints for critical sections that need to be airtight, such as fuel tanks. Once the circumferential welds are complete, the tank is finalized and tested for structural integrity and leak prevention. This integrated process, starting with cutting, rolling, aligning, and welding, ensures that all sections of the rocket are produced to the highest standards, ready to handle the stresses of launch and spaceflight. The rocket features 5 Delphin engines in the first stage, each producing 6,500 pounds of thrust. Once the rocket reaches the edge of the atmosphere, the fairing opens, and the second stage, carrying the payload, is released to complete the journey to orbit. The flexibility of Astra's factory, where the infrastructure is mobile and adaptable, enables them to quickly iterate and scale their rocket production. Their approach draws from advancements in the automotive industry, allowing Astra to continuously refine its rockets without overcomplicating the manufacturing process. This efficient design and production strategy supports Astra's goal of making space access more affordable and reliable for its customers. The Astra spacecraft engine is an advanced Hall effect thruster system designed to provide highly efficient propulsion for spacecraft. Unlike traditional chemical propulsion, Hall effect thrusters deliver low thrust but offer high efficiency, making them ideal for long-duration space missions. The Astra spacecraft engine is designed for various mission-critical operations such as orbit raising, station keeping, obstacle avoidance, and end-of-life deorbiting. Astra's approach to production stands out due to its focus on rapid scalability, reducing typical lead times from years to months, depending on the complexity of the mission and satellite. The engine system is customizable, offering configurations that include multiple thrusters, power processing units, PPUs, and tanks tailored to specific orbital requirements. This integrated approach allows Astra to deliver a cohesive propulsion system where each component is designed to work in unison, eliminating the inefficiencies of procuring and integrating parts from different suppliers. Astra offers two solutions: a fully integrated propulsion system for customers seeking a complete package and a propulsion kit for those who prefer to integrate components themselves. This flexibility ensures that both full-service customers and those seeking faster, customizable solutions benefit from Astra's technology. A key advantage of the Astra spacecraft engine is its space heritage, having successfully completed several missions. With performance metrics such as high thrust and specific impulse (ISP), it is recognized as a reliable and high-performing system in the industry. Additionally, Astra's Sunnyvale facility plays a crucial role in ensuring product quality and efficiency. The co-location of engineering, production, quality, and testing teams allows for streamlined production and enhanced quality control, ensuring that each component is rigorously tested before delivery. This new launch system represents more than just a technological advancement. It signifies a renewed commitment to customers, emphasizing reliability, quality, and rigor. This dedication is reflected in every aspect of design, construction, operations, and the processes that drive the company. The journey culminates in one goal: repeated, successful launches. Initially, Astra focused on speed and demonstrating orbital capability with a mass-producible rocket. Each launch provided critical lessons that informed improvements. Now, with significant experience gained, Astra is consolidating those lessons into a more reliable launch system. Feedback from customers indicated the need for a larger vehicle, which accelerated the development timeline to bring this system to market sooner. The new launch system marks a pivotal step forward, not just in terms of technological evolution but in the approach to product development. This shift, often described as Astra 2.0, redefines how design, verification, and mission execution are handled. The strategy for mission success revolves around four key areas. First, strong reliability controls and redundancy are built in from the design phase. Second, robust verification and validation occur during the qualification phase, ensuring readiness before any launch. Third, stringent quality controls are applied throughout production, including supplier checks and final acceptance testing. Finally, in operations, careful attention is given to ensure safety and preparedness at the launch site. The launch system is a combination of three critical components: the rocket, ground system, and mission control. These systems must work together seamlessly to achieve a successful launch. The vision for mission control is streamlined, with only a flight director and vehicle operator, equipped with the necessary tools for a smooth launch process. Increased automation and efficiency will enable operations to be conducted from anywhere in the world. Rocket 4 incorporates learnings from previous systems into a new architecture that boosts payload capacity and reliability.
Water on.
Designed
7,
for scalable,
6,
cost-effective production, It is a two-stage LOX kerosene rocket with significant propulsion and payload enhancements, aligning with market demands for dedicated, efficient small launches.
The 7 shutdown.
Blue Origin's New Glenn rocket achieved a significant milestone with the completion of its first full-scale 7-meter payload fairing at the company's rocket factory in Cape Canaveral, Florida. This development is part of what promises to be a busy year for the company. New Glenn's first stage is designed for at least 25 flights, a major step towards sustainability and cost savings. Similar to the operation of a commercial airliner, but with cleaner fuel, New Glenn aims to reduce both waste and cost per launch, enhancing affordability and availability for customers. The 7-meter fairing provides customers with twice the volume compared to 5-meter class payload fairings. This larger capacity offers more flexibility in packaging payloads, allowing for new configurations and more ambitious missions. New Glenn's design accommodates a wide variety of payloads and destinations, providing customers with maximum flexibility and significant cost savings. This single configuration helps streamline the launch process while ensuring New Glenn can meet a broad range of customer needs. Powered by liquid hydrogen, New Glenn's upper stage is optimized for high-performance missions. It can carry over 13 metric tons to geostationary transfer orbit, GTO, and 45 metric tons to low Earth orbit, LEO, ensuring it can handle the most demanding payloads. Named after John Glenn, the first American to orbit Earth, the New Glenn rocket reflects Blue Origin's commitment to space exploration. It is designed with the safety and redundancy required to carry humans into space. The rocket represents a key step in Blue Origin's vision of creating a road to space for the benefit of Earth, aligning with their broader mission of making space more accessible and sustainable. Blue Origin's ambitious goals are supported by a dedicated team of engineers, technicians, and electricians working to pave the way for a new era in space exploration. The construction of New Glenn is a significant leap toward making spaceflight more affordable, reusable, and efficient. The Blue Origin-led Human Landing System, SLS, National Team is playing a pivotal role in NASA's Artemis program, which aims to return humans to the Moon. The team consists of major aerospace companies including Lockheed Martin, Northrop Grumman, Draper, and Blue Origin. Each partner brings specialized expertise. Blue Origin is developing the descent element, a cutting-edge lunar landing vehicle, while Lockheed Martin is responsible for the ascent element, which will house the crew. Northrop Grumman provides the transfer element to transport the lander to the Moon's surface, and Draper supplies navigation and control systems, drawing on its Apollo heritage. This integrated system is designed to enable sustainable human exploration of the Moon, using lunar resources to support long-term missions. The Artemis program will land the first woman and the next man on the Moon, with the goal of establishing a permanent human presence. The collaboration of these industry leaders represents a significant step toward humanity's future on the Moon and beyond. The development of the space rocket manufacturing industry has undergone a dramatic transformation since the launch of the first satellite, Sputnik 1, in 1957. Over the decades, it has evolved from a highly specialized government-controlled sector into a multi-billion-dollar global industry driven by private enterprises, commercial markets, and advancements in technology. With growing demand for satellite deployments, space exploration, and interplanetary missions, the industry has witnessed substantial growth, leading to new manufacturing processes, cost reductions, and innovations. The following sections explore the historical context, major players, technological advances, and future prospects of the space rocket manufacturing industry. Early developments and government dominance. The space race between the United States and the Soviet Union in the 1950s and 1960s led to the first significant developments in rocket manufacturing. This era was defined by massive government investments in space programs, with rockets designed primarily for military or exploratory purposes. The most notable achievements included the development of the Saturn V rocket, which was used in the Apollo program to land humans on the Moon. The Saturn V, developed by NASA, was a massive rocket standing 363 feet tall with a liftoff weight of 6.5 million pounds. It had a payload capacity of 140 metric tons to low Earth orbit, LEO, and each launch cost an estimated $1.23 billion in 2023 dollars. During this period, the U.S. government primarily relied on NASA and aerospace contractors like Boeing, Lockheed Martin, and Northrop Grumman. The Soviet Union, meanwhile, developed the R-7 rocket, which launched Sputnik 1. The R-7 family has remained in use for decades, with its descendants, like the Soyuz, continuing to be a workhorse in space missions. The emphasis in this era was on performance and prestige, with less focus on cost efficiency and reusability. Rise of commercial players and cost reduction. The late 1990s and early 2000s marked a pivotal shift in the space rocket manufacturing industry. This period saw the emergence of private companies like SpaceX, Blue Origin, and Rocket Lab, driven by the vision of reducing the cost of access to space and democratizing space travel. SpaceX, founded by Elon Musk in 2002, became a game-changer with its Falcon 1 and later Falcon 9 rockets. The Falcon 9, first launched in 2010, became the first partially reusable rocket to be developed and mass-produced by a private company. The ability to reuse first-stage boosters significantly cut the cost of launches. A Falcon 9 launch costs approximately $67 million, far less than the $152 million for the United Launch Alliance's Atlas V rocket, a key competitor. Falcon 9 can carry 22,800 kilograms to LEO, and the reusability of the booster can reduce costs by up to 30%. By 2024, SpaceX had achieved over 200 successful Falcon 9 launches, marking a shift toward commercialization and affordability. Blue Origin, founded by Jeff Bezos in 2000, also focused on reusable rockets, developing the New Shepard for suborbital flights and New Glenn for orbital missions. Although Blue Origin's rockets have not reached the same level of operational frequency as SpaceX, their manufacturing processes have emphasized advanced composite materials and reusable engines like the BE-4. Rocket Lab, a smaller player, focused on small satellite launches. Their Electron rocket, launched in 2017, offers a more cost-effective solution for smaller payloads, costing $7.5 million per launch and capable of carrying up to 300 kilograms to LEO. By developing a highly efficient manufacturing process involving lightweight carbon composite materials and electric pumps for their Rutherford engine, Rocket Lab has rapidly scaled up its operations. Technological innovations in manufacturing. One of the key drivers of the modern space rocket industry is the improvement in manufacturing technologies. Additive manufacturing, or 3D printing, has revolutionized rocket engine production, reducing costs and production time. Relativity Space, for instance, aims to 3D print 95% of its rockets. The company's Terran 1 rocket is set to cost $12 million per launch, with the entire rocket produced in 60 days using 3D printing technology. This innovation reduces the number of parts in a rocket engine, improving reliability and lowering manufacturing complexity. Another significant advancement has been in propulsion systems. SpaceX's Raptor engine, used in the Starship rocket, employs a full-flow staged combustion cycle using methane and liquid oxygen, LOX, as propellants, making it more efficient than previous engines like the Merlin. Starship, designed to be fully reusable, has a payload capacity of 100 metric tons to LEO. SpaceX aims to drastically reduce the cost per kilogram to orbit to $10, compared to the $2,720 per kilogram for the Falcon 9 and $54,500 per kilogram for the Space Shuttle. Material science advancements have also played a crucial role. Carbon composites, lightweight alloys, and heat-resistant ceramics have been widely adopted in manufacturing rocket bodies and engines, enabling rockets to be lighter and more fuel-efficient. The use of high-strength titanium alloys in critical components, such as SpaceX's grid fins, has enhanced the control and reusability of rockets during landing. Economic impact and market expansion. The global space economy is expected to grow to $1 trillion by 2040, according to Morgan Stanley. Much of this growth will be driven by the satellite industry, with an increasing demand for launches. By 2024, there were over 4,000 active satellites in orbit, and this number is expected to rise to more than 20,000 by 2030, largely due to mega constellation projects like SpaceX's Starlink and Amazon's Project Kuiper. The cost of launching these satellites has dropped dramatically, with SpaceX's Starship promising to bring it down further. The manufacturing industry has responded by scaling up production capabilities. SpaceX's Hawthorne, California factory produces multiple Falcon 9 rockets per year, and the Starship production facility in Boca Chica, Texas, is set to build Starship vehicles at a rapid pace. Other companies, like Relativity Space and Rocket Lab, have also expanded their manufacturing facilities, incorporating automation and lean manufacturing principles to reduce costs and increase production speed. Future prospects. The future of the space rocket manufacturing industry looks promising, with ambitious goals for interplanetary travel and increased commercial activity in space. SpaceX's Starship is expected to be a key enabler for missions to Mars, with the first crewed missions tentatively planned for the late 2020s. NASA's Artemis program aims to return humans to the Moon by 2025, with the help of rockets like the Space Launch System, SLS, and commercial partners like SpaceX. In the near term, the focus will be on making rockets even more reusable and cost-effective. Advances in autonomous manufacturing, 3D printing, and composite materials will continue to drive down costs. Emerging players like Astra and Firefly Aerospace aim to further disrupt the market with cost-efficient launch vehicles tailored for small satellites. The space rocket manufacturing industry is rapidly expanding from a government-dominated field to a diverse, competitive marketplace. The technological advancements, cost reductions, and new business models pioneered by companies like SpaceX, Blue Origin, and Rocket Lab have opened up new possibilities for space exploration, satellite deployment, and commercial ventures in orbit. The next few decades promise even more growth as humanity sets its sights on the Moon, Mars, and beyond. Technicians at NASA's Kennedy Space Center in Florida began the delicate process of transitioning the Space Shuttle Discovery for public display by removing its Forward Reaction Control System (FRCS) in Orbiter Processing Facility 2. The FRCS, a critical component for the shuttle's steering jets while in orbit, controls its orientation and maneuverability in space. As part of Discovery's retirement processing, this system is being carefully cleaned to remove any remaining toxic chemicals used during its active service. The shuttle's fuel and oxidizer chemicals, which powered its jet system, pose potential hazards and must be entirely neutralized before the spacecraft is made safe for museum presentation. This process is a crucial step in preparing the shuttle for its next phase as a historical exhibit. Once the FRCS is fully decontaminated, it will be reinstalled into the shuttle. Discovery will then be restored as an intact spacecraft, preserving the shuttle's appearance and structure for future generations. The effort ensures that the shuttle is both safe for public viewing and retains its authenticity as an iconic space exploration vehicle. Discovery, with its significant contributions to space exploration, including the launch of the Hubble Space Telescope and participation in numerous missions to the International Space Station, will eventually be displayed for public admiration, providing a glimpse into the history of space exploration. NASA's Curiosity rover, part of the Mars Science Laboratory (MSL) mission, began its journey to Mars with the spacecraft launch preparations at the Kennedy Space Center in Florida. The first key components of the mission arrived on May via an Air Force C-17 cargo plane. These components included the cruise stage, backshell, and heat shield. After unloading at Kennedy's Shuttle landing facility, they were transported to the Payload Hazardous Servicing Facility, where initial processing began. Technicians attached a solar array panel to the cruise stage and proceeded with processing the spacecraft's backshell. The backshell is a crucial component that houses the parachute and other essential equipment needed for the rover's entry, descent, and landing sequence on Mars. Together with the heat shield, these two components form the aeroshell that will protect Curiosity during its descent through the Martian atmosphere. The two parts of the aeroshell underwent testing on a spin table before being separated with the help of an overhead crane. In June, the rover itself, along with the descent stage, arrived at Kennedy Space Center aboard another cargo plane. The descent stage is critical for the final landing sequence, as it will guide Curiosity down to the Martian surface. Once at the servicing facility, technicians removed the protective coverings from the descent stage thrusters, inspecting and documenting them in preparation for the mission. The rover was also removed from its protective carrier and placed on a work stand, where it underwent a series of rotation and deployment tests, including checks on its wheels, instrument mast, and science boom. By June 30th, the spacecraft's power generating component, the multi-mission radioisotope thermoelectric generator, arrived at the facility and was moved to storage. Technicians later conducted a fit check of the generator, ensuring it would integrate smoothly with the rover. In parallel with the spacecraft preparation, the launch vehicle, a United Launch Alliance Atlas V, was being readied. The Atlas V rocket, equipped with 4 solid rocket boosters, was tasked with launching the Mars Science Laboratory into space. The rocket's first stage and Centaur's second stage were transported from Port Canaveral to Cape Canaveral Air Force Station and positioned in the integration facility. Over the next few days, the solid rocket boosters and the Centaur upper stage were installed, preparing the rocket for launch. In the payload processing facility, the descent stage was integrated with Curiosity, followed by the encapsulation of the rover inside its back shell. Technicians carefully cleaned the spacecraft's fairing, ensuring it met NASA's stringent planetary protection standards. The crew stage was then joined with the aeroshell, providing solar power and navigation control during the journey to Mars. After final assembly, the spacecraft was enclosed between the two halves of the payload fairing. By November, the entire payload, including the rover and its Atlas V rocket, was transported to Space Launch Complex 41. The payload was lifted into the vertical integration facility, where it was placed atop the rocket and securely attached. The installation of the radioisotope thermoelectric generator marked the final step of Curiosity's Earth-based preparations. With everything in place, the rover and its launch vehicle were now ready for the final leg of their journey, Mars.